What we're going to be talking about today is measuring enthalpy. And enthalpy is the heat of reaction. Remember, enthalpy, the symbol for it is delta H. And this is the heat of a reaction. The sciencey word for it is enthalpy. And in particular, enthalpy is the heat energy released by a reaction at constant pressure. And we talked about last time, that was in contrast to at constant volume. And at constant volume, we called that's the internal energy measurement, because that was the bomb calorimeter. So actually what you're doing today, you're going to be doing something similar to what I'll be talking about in the next couple of slides. You're going to be measuring the heat of a reaction and verifying something called Hess's Law, which I'll talk about in a little bit. But we'll be doing that using calorimetry. And again, calorimetry, if you remember, is just what? Calorie measurement. So it's how we measure heat energy. It's the method in which we do heat energy measurements. So a couple things to point out about calorimetry. The reaction is carried out in a styrofoam cup today. That's our calorimeter. And that's kind of been the standard for like many, many years. The reason we use a styrofoam cup is it insulates from heat loss. So what we're going to be doing is we're going to be looking at a chemical reaction in here. Typically, that's our system. If you did this in Chem 3A or in high school, you probably did it with a piece of metal. And you took a piece of metal and you heated it, and you threw it in the water, and you looked at the temperature change. In that case, the system was the piece of metal. Well, we're going to have a chemical reaction in our system. The other part of this sort of system and surrounding is going to be the water in the calorimeter, or the solution. So a chemical reaction, and then we have the solution that the reaction takes place in. And then what we say is that styrofoam cups are insulators. And what they do is they insulate against heat loss. So heat, and I'll just say energy, just to remind ourselves what that is. So the styrofoam cups insulate against heat energy loss. So we're going to basically say that everything happens in the cup. All the energy is transferred between the chemical reaction and the water. And none of it gets outside. So we're essentially making conservation energy true inside the styrofoam cup. Now, is the styrofoam cup a perfect insulator? No, because like when you go to like a ball game or you're out at night at Christmas and you're Christmas caroling, or you're just camping and it's cold and you get that cup of coffee in a styrofoam cup, what do you always do with it? You hold it like this, right? Because it's warm. Yeah, so it's not perfect, right? But in the short time that we do the chemical reaction, it is pretty good. So for about a few minutes, it's a pretty good approximation of a perfect insulator. It's not quite perfect, so we're going to take that in the lab. We actually take that into account, like how imperfect the calorimeter is. So I'll talk about that when we get ready for the lab. So what we're going to assume is that energy is conserved. So this is conservation of energy. And the law of conservation of energy says heat's neither lost nor gained in a chemical reaction, or any process, really. And so basically what we're saying then is, you know what, here's what we're saying. We're going to say that whatever energy is lost by the reaction, right, is picked up by the solution. And it's exactly the same amount, It's just the signs are different. And that's what this is. Whatever one gains, the other loses. And because we're conserving energy by putting it in an insulated cup, right, we can say it's equal to 0, and we know one is equal to the other but opposite in sign. Now for a solution, we can use the MCAT equation. If we wanted to know how much heat energy was gained or lost by a solution, we would use MCAT. And what's M again? Mass of your solution. C is the specific heat of your solution. And T is the temperature change for the solution. Okay. And temperature change is always going to be T final minus T initial. And then finally, normally what we do in these calculations is we're going to calculate a heat of a reaction, the enthalpy for a chemical reaction, and we usually normalize that. This is the term for getting it to be per mole. So what we do is we figure out how many moles of reaction we have going on, moles of reactant, and it's usually the limiting reactant, and then divide it into the heat. All right. And this is how we're going to calculate. This is the limiting reactant. That's how we're going to calculate the energy for the reaction. So just to give you an example of what the data looks like, because you'll be doing this today. This is an example for an experiment we call the heat of neutralization. It's just the heat of neutralization because it's the energy that's released when you neutralize sodium hydroxide with hydrochloric acid. Okay? So in this particular example, you have a solution containing, all right, 50 grams of 3 molar HCl, and you add it to a calorimeter containing 50 grams of 3 molar NaOH. Okay. So let's see, let me draw my calorimeter. This helps in these problems a lot if you just draw these. That's a horrible calorimeter, but you get the idea. It has a thermometer in it, but I'm not going to draw the thermometer. So I have 3 molar HCl and 3 molar NaOH. And 50 grams of each. And when I mix them together, their initial temperatures, so they're two separate solutions, their initial temperatures are the same. It's 25.74 degrees Celsius. This is my initial. And this is my final. And we're going to calculate the heat energy, the enthalpy for this reaction. Okay. Just a couple of things to start out. What I know is that this is an insulator, right? And so I know there's a Q for a reaction, but I also know there's going to be a Q for the sodium hydroxide plus a Q for the HCl. And that's going to be equal to 0. So this one, because I didn't have just two things, I have 3 different things. I have 2 different solutions and a solid. So for everything that you stick in there, you need a Q value for it, okay? I can still write, because I want to know Q of the reaction to calculate its enthalpy, I can still write this. And what I did is I just subtracted that off of both sides. And so I know if I can figure out the heat energy that is gained by the solution, I can figure out the heat energy for the reaction. So we're going to do something here. On the next slide, there's not enough room to do the whole problem on this slide, but I just wanted to set it up. we know that we can calculate for each one of these. You know Q is equal to mc delta T. And what is given in the problem, they say assume that the solution, right, is that specific heat. There's my C, and here's my density, but it turns out that I don't need it because I just gave you the data in grams. Right. So a lot of times you'll see these problems given with 50 milliliters of this, and I just typically when I have students do calorimetry problems, I just avoid the measuring of volumes. Just tell them just go weigh it, add it to a cup, weigh it, add it to a cup, and that seems to be a lot easier. Okay. So I'm going to do this part last because I want to stick with the calculating of the heat. So I know that delta T for both solutions is going to be 47.10 degrees Celsius minus 25.74 degrees Celsius. Now Q for the HCl would be 50 grams, and I got that from the previous data, right? It's on the other slide on your handout, times 4.18 joules per gram degrees Celsius, and then I just need I need what delta T is, so I'll calculate that out real quick. It's 47.10 minus 25.74. That's 21.36. And that'll be the same for both solutions. They both started at 25.74, and they both ended up at 47.1, because when you mix the two together and the reaction takes place, you can't really keep the two solutions apart. You just get one temperature for the both of them, right? So this is going to be 21.36 degrees Celsius. Now, if you do this calculation for the NaOH, what does it look like? How much sodium hydroxide did you have? 50 grams, right? We're assuming that they have the same specific heat, which is roughly true. And they both underwent the same temperature change because they started at the same temperature, ended at the same temperature. So this is 21.36 degrees Celsius. The reason I'm doing it this way is because it is not always true that heat capacity is the same, and you have to keep those two separate. But in this case, we could have combined it and just called it 100 grams. Okay. So 50.0 times 4.18 times 21.36 is 4,464.24, and I get the same thing for this one. And this is in units of joules because the grams will cancel and the degrees Celsius cancel for all of these. Okay? So I'm going to take and add those two numbers together. And this is the total heat, 8928.48 joules. And this is equal to the Q for the HCl plus the Q for the NaOH. So that's the combined heat energy gained by the two solutions. Sometimes, like if you take a hot solution and a cold solution and you mix them together, they still have the same final temperatures, but their initial temperatures will be different. And that's what we'll be doing today in the lab, actually. So I'll show you that when we do lab. Right. So this number is the heat for the reaction. Right? It's not the enthalpy, because enthalpy is usually per mole. And so to calculate delta H, so this is heat. So we know Q for the reaction is equal to the negative of the Q of the NaOH plus the Q of the HCl. That's what we have from up here, the bottom of the slide. Forgot to bring my water. So this is actually equal to negative 8928.48 joules. So if I want delta H for the reaction, that's going to be Q for the reaction divided by N for the reaction. And that's going to be the moles of the limiting reactant. Now we have to calculate the moles of the limiting reactant. How am I going to do that? What data do I give you to calculate moles? All right, if you go back up here, I have this information. Now, in this case, I can use either one. The stoichiometry is 1 to 1, and I gave you the same amount of each. Okay, so one of those can be considered the limiting reactant. So I have 50 grams of HCl. This is going to be for the moles of HCl. It's 1.00 ml, or sorry, 1 ml per 1 point, and it's down here. 0.0 grams times 10 to the minus third liters per milliliter, like that. So I got my millis to cancel, I got my grams to cancel, and that should leave me, oh wait, liters. I want moles though. So then I got to multiply by 3.00 moles per liter. I'll do that calculation real quick. 0.05 times 3. That comes out to be 0.15 moles. Let me double check that calculation. Yeah, 0.15 moles. 3 significant figures, actually. Yeah. So that's one of my limiting reactants. And I'll go down here. And I'll go 8928.48 joules per 0.150 moles. That comes out to be 59,523 joules, which would probably convert to kilojoules. That's a more standard unit for this kind of stuff, per mole. That's 59.5 kilojoules per mole. Okay. So this is how, if you need to know, calculate the heat of a reaction, you would calculate the enthalpy of reaction from calorimetry data. You'll get some practice with it in the lab today, and like I said, we'll do more examples when I get there. So I want to talk a little bit. Any questions on like how that's done? Yeah. There's a lot of little calculations in that. Take the time to do it a few times just to make sure you can see where everything comes from. But keep in mind what you're trying to do. You want the heat of the reaction, so you'd be doing MCAT, that kind of stuff. Oh, yeah. Negative. Carry that negative through. This, she says, you didn't do the negative. That's a negative. That's a negative. That's a negative. Oh, so what does that number tell me, by the way? What's the negative mean? So the reaction, what's that? Yeah, it's giving heat away. It's losing that much energy. So what the negative is telling me for the reaction, in order for the water to heat up, right, the reaction had to give up that much energy. And that's why the water got hot. The water gained that much energy, the positive of that number. So yeah, anytime you get a problem like this, think about it in a series of steps. Figure out how much heat energy there is. Most of the time there's an MCAT equation. Right? Do a conservation of energy so you know like what the energy is coming from, and then divide by the number of moles. So you need to find the number of moles and divide. Okay. So Hess's law actually has a lot to it, but it is actually pretty straightforward. Hess's law has to do with thermochemical equations and how the energy relates to how we write the reaction. Okay? So I'll give you just a really quick, sort of simple example. This is what Hess's law would be. Let's say you drive your car and you have a gallon of gas. Right? How far does somebody drive on a gallon of gas? What's your gas mileage? 21? Yeah. So what if you get 2 gallons? Yeah. That's Hess's law. All right. Heats of reaction are additive. Like you can add reactions up, and if you can add them and make another reaction, like instead of going for 1 gallon, you're going for 2 gallons, then right, that's Hess's law. You're going 42 miles on 2 gallons of gas. Now, it kind of works a little different because this is not like exactly like driving a car. Because you notice I have H2O liquid goes to H2O gas, and that's plus 44 kilojoules. So the plus means in order to get it from liquid to the gas state, it has to absorb energy, right? What if I write it backwards? Yeah, it's minus, right? So unlike your car, you can't push your car 21 miles and get a gallon of gas to come out of it. But that's what that would be the equivalent of, right? It'd be cool if you could do it because I'd be making my kids push the car around the block all the time. So you got to pay for your gas the hard way. Yeah, so this would just be minus 44 kilojoules. Okay. Now, if you wanted to melt ice, this is how much energy it takes. 6.02 kilojoules per mole of water to melt the ice. So when it's at its freezing point and you want to melt it, that's how much energy it takes. But let's say you had those two numbers. You had the H2O liquid to H2O gas is 44 kilojoules. And the H2O solid to H2O liquid was 6.02 kilojoules. And then you wanted to know how much energy it took to go from solid to liquid, or solid to gas, right? How would you do that? What's that? You can add them? No, it's not double. Think about it like this. I have H2O. I was going to write it on here, but I don't think I will. Yeah, I'll skip it. To go from solid, right, to liquid, it takes this much energy, right? But if you want to go from liquid to gas, it takes this much energy, right? No, just add it together. Just like if you doubled your gas, right? Yeah, you're just adding it together, and then the total is like 50.02 kilojoules. Like, it's basically saying, if I wrote solid, liquid, and then, it's a gas out here. and I'm walking, right? And I take a step, that's the solid, the liquid. And then the liquid to gas, I gotta walk this far. And then I ask you, how many steps did it take me to walk the whole way? She said, well, add your steps up, that's all I'm doing. Even though I didn't do it all at one time. And Hess became famous for this idea. Okay, so let me show you how to do it on paper. So I have H2O solid, and you got to keep track of states when you do this. Goes to H2O gas, or liquid, sorry. That's 6.02 kilojoules. And then I have H2O liquid, goes to H2O gas, that's 44 kilojoules. Right? When I add these two reactions together, what can I get rid of? Yeah, I'll have liquid on one side and I'll have liquid on the other side. If you just add them up, you're going to get this, and don't cancel. You get this H2O solid plus H2O liquid goes to H2O liquid goes plus H2O gas, like that. But see, these are the same on both sides. So they don't have any effect on the energy because it didn't on one side and the other side is exactly the same. So this adds up to be, with sig figs, 50 kilojoules. So that's how much energy it takes to literally go directly from the solid to the gas. So this heat of sublimation. And when you go from solid to gas state, that's a sublimation. And what Hess says is that you could figure out the heat for any reaction as long as you can add other reactions up to get there. So if you know different reactions and you know their heats, you can combine them to figure out heats for reactions you can't do. I'm going to skip this. I talked about it. It's like walking. Okay, this one's a little more complicated because, of course, it gets more complicated. And my analogy for this is, and what I want to do is I want to give you like a means to approach these problems. Because even though they look complicated, in the end, usually everything you don't need cancels out. It's like balancing equations, like when you put the one coefficient in front of the last thing and everything balances. That's how these problems work, but you have to know how to start them, okay? So I always ask this question, when you do a jigsaw puzzle, what are the first pieces you look for? The corners and then the edges, right? I read a study somewhere, I know because people study these things, how people think, and that's only in the United States. In other countries, they start with the patterns in the middle. I know, it's messed up. Right? I want to be systematic. I find corners, and then I look at the picture, and I know where the corners are, right? So I know this corner's here, this corner's here, this corner. And then I take all the edge pieces, and I sort them out and put all the other pieces back in the box, because they're in my way. And I try to make sure, like, from the picture, I know this edge piece goes over on the left side, and this one goes on the top, this one goes on the right, this one goes on the bottom. And that's sort of the process for jigsaw puzzles, right? It's going to be the same process for this. The picture is the equation that you're looking for. It's this one down here. And you know that H2O2 has to be on the right side of the picture. And H2 and O2 have to end up on the left side of the picture. And you'll be given a series of reactions to put that picture together. Now, unlike a jigsaw puzzle, when you only have the pieces you need, right? Sometimes you get extra pieces. It's like the jigsaw puzzles at my house because I have kids. They just don't put them away right. Sometimes I have a jigsaw puzzle that the bases are this way. Okay, so we'll look at this. What goes on the left and what goes on the right? Right? You have to pay attention to that. The reactants. Right? Let's start with H2O2. Now look at the givens, right? Which reaction is the H2O2? The very first one, right? Let's do this. This is 1 and 2, and this is 3, okay? So in reaction 3, right, I can look at H2O2. That's the right edge of my picture. It's in the left side of that equation. So what I have to do is I have to flip it around. So what I'm going to do is I'm going to go H2O liquid plus 1/2 O2 makes H2O2. Oh, I'm sorry, I left the state out for oxygen, but that's gas. H2O2 liquid. Now, so that's -1. That's, I took equation 1 and I flipped it around, right? And so the energy for that is what? Delta H is, say it loud because I still can't hear. 98, because I flipped it around. Remember, if it's 98 one way and I flip it around, it's got to be the opposite side, plus 98. So far, so good. Now, I have H2 and O2. Right? In the second in equation 2, I have H2 and O2, and they make water. Now, where do those have to go in equation 3? They're still on the left, right? Now, what would happen if I just took equation 2 and added it to the equation -1, and I call it -1? You know, the last equation. What would happen? I'd have like too much stuff, right? How many H? Yeah, I'd have too much stuff. What? How many H2s do I need? I need 1, right? But there's 2 in that equation. So I'm looking at the left side of the picture, right? Left side of the picture says, I don't have any H2s there. So I know I need to have H2, but there's too much up there. So what should I do to it? Half it. Just cut it in half. You can do this. So I'm going to say, I know, 1 H2. So this is 1/2, not negative, just 1/2 of equation 2. Just keeping track. What does that give me for oxygen? 1/2 oxygen, right? This is gas, and this is gas. And what does that give me for waters on the right? 1 water. And what is that energy going to be, you think? Half. And I don't change the sign because I didn't flip it around. And then I'm going to just divide it by 2. I'll deal with the math later. Okay. Well, that, I'm just going to divide it by 2. Now look what happens if you add these equations up. I'm going to draw a line here, so I'm going to add these together. I'm going to use blue to cancel stuff out. You guys see anything that cancels out? What? What? Gas? But which substances cancel? Like looking at the 1/2 O? Well, they don't cancel, but they add, right? So I can add 1/2 and 1/2, and I get a whole, right? That's an O2. is there anything on the left and the right that are the same? Remember spectator ions, right? What's that? H2O? H2O. And so what am I left with? On the left side, I just have H2 gas, right? Plus O2 makes H2O2 liquid. So that's the reaction that I was looking for. And all that extra stuff just disappeared. Added together, all the weird stuff went away, and you ended up with the reaction you wanted. And what Hess's law says is if I can add two reactions to get a third, right? The heats of reaction are additive. I can get the heat of that reaction. So all I have to do is take 98 and add it to half of negative 571.6, and that'll give me my enthalpy for the reaction. Okay, 98. Actually, I'll do the other one first. 571.6 negative divided by 2, and I'm going to add 98 to it. Yeah, negative 187.8, I hope. And this is how we find heats of lots of reactions that we don't know how to do yet. Like if you want to make something and you don't know how much energy it's going to take, or it's going to even require energy, or give off energy, right? We can figure out a lot of that by doing calculations like this. So Hess's law just simply states heats of reactions are additive. That's all it states. Okay, we're going to do one more. Did I leave space on another page? Oh, I did not. I might have to add a slide after this one. Hang on. Okay. Wrong orientation. That's fine. I stole this. I like this problem. I stole it from a textbook years ago. Self-contact. Horribly scanned. Okay. What is the heat of the reaction at constant pressure? That means that use the following thermochemical equation. So we need to know the reaction that's at the top. So that's my picture, right? So we know what's on the left side and what's on the right side, where stuff is supposed to end up. What should I start with? Which are the corner pieces or the edge pieces? Second one? Yeah. This one? Well, I was asking more generally, you got the right idea. Yeah, that are, oops, shoots. Like corner pieces, edge pieces, whatever you want to call them. One of them's this. Right, now, and let's find another, see if there's another one we can use. First one by 2. Yeah? Yeah? There's another one, right? It's here. An H2O. Now, why can't she like rattle these off so quick? Because they only occur in one equation. So, right? Edge pieces only go on one side. Now, if you have two pieces that are completely white in a puzzle, right? You don't know if it's on the left side or the right side, or the top or the bottom, right? So those are all unique in this process. The NO is unique. It only occurs once down. The NH3 is unique. It only occurs once down in the bottom reaction. The H2O is also unique. It only occurs once. So this is what we're going to do. We're just going to take it blindly write all these things out and then just cancel everything and see what we end up with. Okay. So I'm going to roll this down. Okay, so first thing, I'm going to take this reaction. I need to. This is the hardest one to do. I got to flip it and double it. All right. So I'm going to go 2 and 8, and you can work ahead of me if you know what you're doing. Oh, and I'm going to leave the gas state out because they're all in the gas state. I love these when you don't have multiple states because then you don't have to keep track. Because sometimes you get O2 liquid, O2 gas, and then you got to keep track of all that stuff. So I'm going to work, you work. Oh, and I got to double it. 4NH3, 6H2, 2, N2, and then delta H is going to be plus 91.8 times 2 kilojoules. I changed the sign and I doubled it. Now the NO has to be doubled as well, but I don't have to flip it. So I'm going to say it's 2N2 plus 2O2 makes 4NO, and that's going to be 180.6 times 2 kilojoules. And the sign doesn't change, it's still positive. And if it's annoying you, you can't cancel stuff out at this point. But I'm just going to do it all at one time. And then the H2O is also in the correct position. It's on the right-hand side. But I need to triple that. Because if you look at the top reaction, there's 3 H2Os. In the bottom reaction, there's 2 H2Os. So I got to triple that. So I'm going to go 6 H2s plus 3 O2s makes 6 H2Os. And this is minus 483.7 times 3 kilojoules. Now let's see if that worked. And you always have to check, because sometimes in the trickier problems they make you find another reaction. And so then you have to go back and find that other reaction. Okay. I'll put my blue canceling pen on. What looks like like the spectator island? What's the same on both sides? The 2 N2s? Cool. 6 H2s. That's it. So what I'm left with, 4 NH3s plus 5 O2s, gas, right, makes 4 NOs plus 6 H2Os. And then we compare that to what we were told to find. And it's the same. So then honestly, this is where people have the worst time, is adding those numbers together, because they'll forget a sign or they'll forget to multiply it. Okay. So if it helps you, just write it all out, like 91.8 times 2 plus 180.6 times 2 and minus, because I'm going to add, well, let me do this, plus a negative 483.7 times 3 kilojoules. And just work through all the math that way. Find each section, add it together. So 91.8 times 2 plus 180.6 times 2. That's 544 minus 483.7 change sign times 3. That's a big number. Let's see if I did it right. 1,995.9 kilojoules. Yeah, let's keep that as a 660. Did I screw it up? Oh, I know what I did. I screwed it up. No, I didn't write the answer down. I know what I did. I'll show you in a second. $906.3. Yeah, I put minus and negative instead of just adding it. Again, Hess's law just says once you have the energies, just add them together. And in my head, I put minus the negative, and it blew up on me. Okay. Negative. I'm going to skip that for now. I'll talk about it later. Okay. Because I felt like it. Wait. So, sorry, gotta go back up here. How many H2Os are in the picture? Like the first reaction? 3, right? And I had in the puzzle piece, I only had 2. So I just multiply by 3 to get this 6. So identify the puzzle piece is a very important part. All right. So it would be really horrible if you had to do this all the time. Like if every time you had to figure out the heat of a reaction, you had to find 3 reactions that you could combine to get the energy that you needed. So this is what they've done. They've created standard enthalpies of formation. So what does that mean, right? Well, the standard enthalpy of formation is the energy, right? Hang on, let me write it out here. I'll just rewrite the definition. Standard enthalpy of formation. It has some symbols that are important. Delta, H, F, and a naught at the 0 like that. The F is for the formation, and the naught is for standard states. And I apologize because chemists didn't use like standard STP, standard state. They didn't use that. They have a whole different standard state. F is for formation. And the standard enthalpy of formation is the energy required to form 1 mole of a substance from its reference forms. Now I have to explain a couple of words in there. So basically, if you just in general thought process, it's how much energy it takes to make 1 mole. Now the reference forms are the forms typically are from the elements in their pure state. Typically that's what it is. Okay? It's the amount of energy it takes to form substances from the elements in their pure states. Now it's a little more technical than that, and I'll talk about that in a second. So if you wanted to make, if you had these 3 elements together, you could make this combination. That could be a reaction. The reference forms for carbon are graphite. The reference form for hydrogen is H2 gas. And the reference form for oxygen is O2 gas. Okay? And they take those things, they mix them together, and they get a reaction, and this is what they get. It's negative 483 kilojoules So it means that process would be exothermic and release 483 kilojoules. You can take these same three elements and combine them and make two H2s and two CO2s from the reference form, right? So we use these reference forms and we figure out how to make a whole bunch of stuff. And then to calculate the energy of a reaction, all you have to do is figure out what the difference is in energy. So if you wanted to do carbon solid with H2O gas to make hydrogen gas and carbon dioxide gas, all you have to do is to know how much it takes to form the reactants in the reference forms, the products from the reference forms, and then you just subtract and you get the difference in energy. So in this case, if you wanted to calculate delta H for the reaction, that's this reaction here, it's the delta H's for the products minus the delta H's for the reactants. And so it's final state minus the initial state. So it's going to be, oh shoot, zoomed in a little bit. It's going to be minus 393 kilojoules minus, in this case, a minus 483.6 kilojoules. And that gives us 90.1 kilojoules. So let's do an example problem. Oh, let me talk about standard conditions. So what standard conditions mean? It means pure solid, pure liquid, or gases at 1 atmosphere pressure. Okay? And for solution, it means 1 molar. So this is what we mean by standard state. And standard state, there's no temperature reference. So you know, like STP is actually 0 degrees Celsius. There's not such a thing for standard states. They sometimes will have, you have to look at the tables that you use to see what temperature you use. Typically it's 25 degrees because it's room temperature, but that's not part of the standard. Okay. And then the standard enthalpy of formation, right, is for these substances at their standard states to form 1 mole of a substance at its standard state. So the reference forms when combined, right, at standard states to form the product at standard state. So I said oxygen's reference form is what? O2. And it's gas, right? Why do you think we use that? Yeah, it's actually the simplest, most stable form of oxygen in our atmosphere. They could have used this too, but they didn't. Right, that's ozone. And these actually together, these are known as the allotropes of oxygen. And I'm just telling you this word because it's important that you know this kind of definition. But they pick one of the allotropes of an element to be the reference form. And for O2 gas, what they say is delta H of formation is equal to 0. They arbitrarily took the universe, okay, and reset its bank account to 0 and said all the elements in the reference forms have $0 in them, 0 energy in them. And then do all the calculations based on that idea that the reference forms have 0 energy. Now, do they really have 0 energy? No, nothing really has 0 energy, right? But we do it as a bookkeeping method. So you know how when you're a student and you have problems with money, right? And you're in debt, right? Right? Because she's laughing. It's like the universe, the chemist said, well, we know some of you are negative and some of you positive, all you allotropes. We're just going to call you all 0 and make you the same. Okay? That's how we do that. So we're going to do, and this is the whole idea of product minus reactants, but that's an annoying equation, and I can't even tell you why I think that. So here's what we're going to do. We're going to calculate the heat of combustion. These are standard enthalpies of formation for some different substances. And I'm going to do for the combustion of, let's see what I have up there, methanol. So I'm going to do heat of combustion for methanol. We're going to calculate it using standard enthalpies. So first of all, I have to have an equation. So I'm going to say CH3OH liquid plus, what's the combustion reaction need? O2, gas. And what's it going to make? CO2 water. Many of you read carbon monoxide and didn't think about it and just marked that. Just like, oh. And now you're all kicking yourself. It's okay. I get it. And we're going to do CO2 gas and H2O liquid. Because heats of combustions are typically to the liquid form of water. And we want to calculate delta H for this. So first thing I have to do is balance the reaction. So I have one carbon dioxide because I have CH3OH plus O2, right? And I have one carbon. How many hydrogen should I need? 4, yeah. So 2 goes in front of the H2O. And then I got to count up my oxygens. And I need I need 5. Well, I don't need 5. I have 4 on the right, right? And I have already 1 on the left. So what I need is, just to make this fun, this is total of 4. There's 1, so I need 3 more. So this is the 3/2. So now what I'm going to do is double everything and get rid of that stupid coefficient. I'm going to have 2 CH3OH liquid plus 3 O2 gas makes 2 CO2 gases plus 2 H2O, or 4 H2O liquid. And normally what I do, and this is what I tell students to do, is write, because this is where people make a lot of mistakes, write the energies, standard enthalpies of formation under each one. So for CH3OH, it's minus 238.7. And I'm just put kilojoules out here because I get tired of writing the unit and jamming it in there. And for oxygen, it's 0, right? That's the reference form for oxygen, so we'll just call that 0. For CO2 gas, what is it? Yeah, minus 393.5. And for waters in the liquid state, right? So that's 285.8 negative. Now think about how this is going to have to work. It has to be, you have to calculate it for every mole of substance. So I have a 2 here, right? So I'm going to have to multiply that by 2. This one's multiplied by 3, but it's 0, so it doesn't matter. The CO2, I'll multiply it by 2. And for the H2O, I'll multiply it by 4. So what I'm doing is I'm taking into account the stoichiometric coefficients. Because that's how much of it I made. Remember, the enthalpies of formation are per mole of substance, but I have 4 moles in the reaction, so I can multiply by 4. This is the next thing I have students do. Just calculate what the 2 numbers are separately. And a lot of students will go through and calculate each one and then put them together. But you're going to add everything in the reactants and everything in the product separately, but together. So negative 2 238.7 times 2. Well, that's not it. 238.7 times 2. That's negative 477.4 kilojoules. This one's 0, so I don't worry about that one. I'll get rid of it. In fact, I won't even write it. And the other side is negative 393.5 times 2 plus 285.8 times 4. I get negative 1930.2, and this is in kilojoules. So, in a sense, this is the enthalpy that's required to form, that goes along with the formation of the products. This is the enthalpy for the formation of the reactants. And to get the difference in energy, delta H of the reaction, it's going to be negative 1930.2 minus a negative 477.4 kilojoules. This is products. This is reactants. And I end up with negative 1,452.8. Just a picture of what's going on, like I had the picture before. I have reactants. And to go from reference forms to reactants is minus 477.4 kilojoules. And to go to the products, this is minus 1,930.2 kilojoules. If I want to know the difference of energy in reactants and products, I just have to subtract those two numbers. So that's what I did. I mean, pictorially, what I did with the numbers. To get this energy change, it's products minus the reactants. In other words, though, products are lower in energy than the reactants. That's what that means. And really, it's just like bookkeeping and trying to figure out how much further down the products are, how much further up the products are. Oh, well, that's it. Oh, that's just right on time. So that kind of summarizes that whole chapter. A lot of practice.